All right. Hi, everyone. My name is Alina, and I'm going to be walking through a review of the chain rule. So I'm going to start with the definition, and that is that for multivariable functions, the chain rule gives us a way to differentiate a composite function, Now, what is a composite function? Well, say we have a function z, and we're given that z is a function of x and of y. So x and y are two distinct variables. And say we're also given that x and y are both functions of the third variable, t. Then indirectly, we have that z is also a function of t and can be differentiated with respect to t. So the chain rule gives us a way to differentiate z indirectly with respect to t. More mathematically, you have z equals a function of x and y. And if you've got x as a function of t, but a different function, so you've got g of t, not f of t. And then y is a function of t, but different from x, so you've got y equals h of t. Then z is, if you just switch out, y equals h of t and x equals g of t, then you've got z equals a function of g of t and h of t. And this right here is a composite function. So now that we know this, we can get started, and I'm going to walk through, kind of like we did in class, I'm going to walk through a couple cases of how we use the chain rule before I can walk through, a more general application of the chain rule, as in, a general rule that you can use for any type of problem. And then at the very end, we'll walk through a more complicated example. So for the first case, in special case number 1, we have that x and y are each functions of a single variable t. So notice that here it is a single variable t. So if you've got z is a function of x and y, x is a function of t, and y is a function of t, what we're trying to find is dz dt. In other words, we're trying to find how we can differentiate z in terms of t. So the way we do that is we build a tree. So the first thing we have is it's like the mother function. Z is a function of both x and y. So what I have here is you kind of start with z, and then you draw branches like these to the variables that z is a function of. So z is a function of x and y. So we draw kind of two branches here to x and y. And then we do the same thing for x and y. So if x is a function of t and just t, a single variable, then you draw a straight branch down to t. And if y is a function of t, then you can also draw a straight branch down to t. So how you build the tree is you basically take a function and then draw branches to what that function is a function of. And we did that for z, x, and y. Now, how do we find dz dt? Well, the chain rule tells us that if we multiply, I'm going to use a different color here, if we multiply down one branch to get to this kind of what I call like this kind of leg of dz dt, we have to add it to the other leg. The other way we can kind of get dz dt through the y path, say y path, just kind of informally in the x path. If you do that, and you do that, you multiply down each leg and you add them together, you get dz dt. So let's walk through how we do that. You have the first branch. To multiply down it, number 1, you have to take the partial derivative of this leg. Well, that would just be the partial with respect to x. And notice I'm using partial and not d because z is a function of two variables, not just one. Whereas here, x is a function of just t. So you can say dx dt. And what you have here is partial with respect to y. And then you've got dy dt. So what you have is you want to multiply down this branch. And so what that means is you multiply this term with this term. 1 times 2. So you get dz dx times dx dt. And do the same thing for the other branch. So let's use maybe a different color here. You got to multiply, so you do partial with respect to y times dy dt. And what you do is you add those together. So you take this term and this term, y branch and x branch, and you add them together. So if you notice, we can write that in a more clean way here. Partial of z with respect to x times dx dt plus partial with respect to y times dy dt. It's pretty simple. You just have to multiply down each branch and then add them together. So we can even call this like the orange branch, and we can call this one the green branch because we highlighted those in those colors. Which brings me to special case number 2. So earlier we did z is a function of x and y, and then x and y are both functions of one variable, t. Let's go back to my blue here. One variable, t. Now we want to do when x and y are each functions of two variables, s and t. So instead of one, we have two variables now. So you kind of set up the tree as before, but in this time, you have two indirect derivatives you can find by the end. The first one is dz ds. Because x and y are each a variable of s, a function of s, excuse me. You can also find dz dt, kind of like before, because x and y are also functions of t. So you've got two, kind of paths that you can do here. So let's try to find dz dt first. Let's focus on that. So we set up the tree. Remember how you set it up? You've got the z, which is a function of x and y. And then x and y are each functions of two variables, s and t. Functions of two variables, s and t. I'm going to undo that so it doesn't get too crowded. So what we're going to do in order to find dz dt is, well, let's multiply down the paths again. I'm going to use orange for dz dt. So you want to multiply down here. But then in order to get to t, you have to take this branch down here. And the same thing over here. You start here and then you go down to t. So if you notice, you kind of end at t on both legs. So if I use orange again, this leg right here is dz dx. This leg right here is, and here we use partial with respect to t because x is a function of two variables. Here you've got dz dy, and here you've got dy dt. And you do the same thing you did before, is you multiply down here, and then you add them together. So to multiply down, you've got partial with respect to x, and then partial of x with respect to t, and you want to add that. You want to add that to partial with respect to y times partial of y with respect to t. And that is your formula for dz dt. You've got dz partial of z with respect to x times partial of x with respect to t plus partial with respect to y times partial with respect to t. Now, if that is your dz dt, I think it's pretty clear how you can get your dz ds. You do the same thing. Let's do green. To get to s, here is the first way to get there, and here is the second way. You kind of just have to flow it down. It's kind of like a river. You kind of take the fork that takes you to s or to t. So if you start at z and you know you want to eventually get to s, you pick one of the ways and then pick which way that gets you to s, and then you do it for the other fork. So here, notice that this leg stays the same. It's still dz dx, or excuse me, partial with respect to x. And same thing with this leg. What changes is this bottom leg. You've got now dx ds. I'm actually going to make that a darker font just to make sure that people can read it. Dx ds. And here on the other side, you have partial of y with respect to s. I meant to say partial here as well. So now notice that because these two stay the same, what you end up getting for dz ds is, again, the first half is the same, partial with respect to x, but now you've got partial of x with respect to s plus partial of y times the partial of t. So you can kind of, let me see if I can do this without getting it too crowded. I'm going to erase this part so you can see we kind of do the same thing here. We multiply down this leg and this leg, and then what we do is we do 1 plus 2. Make sense? So after this, I can, now that we've walked through, x and y being both functions of just a single variable, and then each a function of two different variables, now we can kind of talk about the chain rule more generally. And that is that you can really have any number of variables and any number of layers to this tree that you build. And that x and y don't necessarily, or whatever variables you use, they don't necessarily have to even have the same variables. Like x could be a function of s and y could be a function of t. So if you wanted to find dz dt, you would just go down the y leg. You wouldn't have an x leg to go down. So in order to visualize this a little bit, I've kind of put together a tree already, and we can maybe reverse engineer this and find like what the functions are. And so we've got the very top function u. So automatically we can see that directly u is a function of, we've got three variables, x, y, and z. X, y, and z. Now let's look at what x, y, and z are each a function of. So x, I can see three variables that x is a function of. So x is a function of r, s, and t. And it looks like those same three variables are what y and z are each functions of as well. So I'm going to do y is a function of r, s, and t. We're going to go z is a function of r, s, and t. Perfect. So what you want to do is, I've only decided we can only find maybe one right now, because really, like, if you think about it, du ds, there are multiple partials or multiple du's we can find here, right? We can find du dr, which is 1. So we can find 1 du dr. 2, we can find du ds. And 3, we can find du dt. And where am I getting these from? Well, the very bottom of the chain, you kind of have r, s, and t as your only three variables there. So you can find at the very bottom, du's of each of these. And I've decided to work through how we can find du ds here. And the other two I'm going to leave alone just for the sake of time. So for du ds, I've already kind of multiplied it out here, but maybe we can fill in the tree part. So here we have du ds. How do we get there? Well, like I said, follow one fork. So if we follow the x fork, we want to get to du ds, so we go down where it takes us to s. If we follow the y fork, we do the same thing to s, and z fork, we get to s as well. So what we want to do now is we want to take each of these legs, find the partials that make up each branch. So this is partial with respect to x. This is partial of x with respect to s. It seems to be partial with respect to y, partial of y with respect to s, and partial of u with respect to z, and partial of z with respect to s. Notice that we have now all of the ways to get to s are accounted for. We can add them together after we multiply down each leg. So multiply, add, multiply, add, multiply. So take 1, 2, and 3. I'm just numbering each leg and add them together. So if we notice, this gets us leg 1. That gives us du dx times dx ds. You add that to leg 2, and you add that to leg 3. Partial of y times partial of s is 2. Partial of z times partial of s is leg 3. And this is how you get, from u to s. That's how you get du ds. So now that we know the general way that the chain rule works, we can work through a more complicated example. So here's my example. If u equals x fourth y plus y squared z cubed, x equals rs e to the t, y equals rs squared e to the negative t, and z equals r squared s sine of t, what is du ds? So that's the first question. What is the partial of u with respect to s? And I know I'm not supposed to be saying du ds, partial of u with respect to s. I'm just going to start saying partial with respect to s in order to keep it clear. What is partial of u with respect to s when r equals 2, s equals 1, and t equals 0? So what is this asking? This is asking two things. First, what is the partial with respect to s? And the second is, what is that value? What value does this take on when R is 2, S is 1, and T equals 0? So clearly, we have to find this and then plug in these numbers in order to get that final value. So let's start building our tree. I'm going to use blue here. We know that U seems to be a function of 3 variables, X, Y, and Z. So I'm going to put that here, X, Y, and Z. And now X seems to be a function of 3 variables as well, R, S, and T. Notice that E is just the number E. So you've got R, S, and T. Going over to Y, R, S, and T, and going over to Z is the same, R, S, and T. So we're going to put those legs here, R, S, T, R, S, T. Seems like I've run out of room, oh well. Now, it's looking for du ds, partial of u with respect to s. So let's follow the trail to get there. We have this and this. So these are all the ways we can get to s, right? And if we solve for the branches, or if we calculate out the branches, it's du, dx, etc., etc., etc. I'm not going to write those all out because we've done them before. But we can look at this and see, like, okay, so leg 1, if we number this is leg 1, this is leg 2, and this is leg 3. We can write this out as partial with respect to x times the partial of x with respect to s. And if you fill in the tree on your own, you'll be able to see that that is leg 1. You want to add that to leg 2. Notice that that is leg 2. And the last part is this. And again, this is leg 1 added to leg 2 added to leg 3. And again, take a look at the tree, see if you can calculate each of these on your own. We've kind of walked through them already, so I figure we're good to go on that. Now, I've already kind of calculated each of these partials just because I wanted to save time and make sure that the math was right, but I can walk you through one of them at least. So the partial of u with respect to x, we've done these. It's just simple partial derivatives. That's clearly 4x cubed. Get rid of the and y, because y is a constant right here, so it's 4x cubed y, and there's no x in this term, so it's a constant, so that's 0. That's how I got, partial of u with respect to x. We can even do partial of x with respect to t just to make things clear. So what you do is you treat everything else besides s as a constant, so that derivative ends up being re to the t, which is exactly what I've written right here, re to the t. So I've already gone through and calculated all the partials. I would recommend doing them on your own just to make sure you have a hang of it, but they're all written down here. So the next step I want to do is, now that we have all of our partials, we've got every piece of the puzzle up here that we need to solve partial of u with respect to s. What we want to do is now plug in all of the numbers that get us x, y, r, t, etc. Now, we were given r, s, and t, right? We were given r is equal to 2, s is equal to 1, and t is equal to 0. These were all given. I should probably go back to blue so that we don't confuse. What we had to solve for are these variables, x and y and z. So we are given equations for all of these conveniently. X is rs e to the t, y is rs squared e to the negative t, so on and so forth. So plugging this in, if you plug in r is 2, s is 1, and 0 is t here, you end up getting x is equal to 2. You plug in the rest for y and z, and you can get y is equal to 2 and z is equal to 0. Again, I've done that math already just to speed things up here. It should be pretty straightforward, plug and chug. And from here, all you want to do now is plug them into each of these terms, plug all of these numbers into each of these terms in order to get your final answer. So if we know that x and y are each equal to 2, this just ends up being 4 times 2 cubed, which is 8, times 2. This ends up being r, which is 2e to the 0th, which is equal to 2. 8 times 4 is 32, times 2 is 64. This one right here ends up being 2 to the 4th, plus 2 times, we know that y is 2, and we know that z is 0, so this term will just end up being 0. Yeah, so 2 times 2, that should be 16. Here we have, again, plug and chug, 2 times r, which is, what is our r? Our r is 2, times our s, which is 1, times our e to the 0th, which is equal to 4. I know it's tedious, but we're almost there. We've got 3 times y squared, y is 2. So you've got 3 times 2 squared times 0 squared, which ends up, of course, just being 0. And then finally r squared, so you've got 2 squared sine of 0, which again is just, well, actually t is 0, yeah, so which again is just 0. So we have numbers here. We can just make these equal to 0, equal to 0. So now it's just plugging it all in. So if we know that, here's what I'm going to do. I'm going to copy and paste this. If we know that du ds is equal to all of these terms, we can just plug in for each of these terms now. So du ds is equal to, what is partial with respect to x? We found that to be 64. 64 times what is partial of x with respect to s? That apparently is 2. Plus what is partial with respect to y? 16. And then that will be 4. So plus 16 times 4. And finally, what is partial with respect to z? 0 times 0, which is just 0. And that gets you 128 plus 64, which, let me do some mental math here. This should be your final answer. Yep. So we have 192, which is your value of partial of u with respect to s. So notice, I'm just going to quickly recap how we found that. We built a tree in order to get, show us how the chain rule works. We built a tree for partial of u with respect to s. We followed the paths to get to partial of u with respect to s. We added all of those paths together. And then we found what x, y, z, r, s, and t, what those values all were by plugging in r, s, and t into the equations of x, y, and z. And finally, we plugged in all of these numbers into each of these equations in order to get what the values of each of these were, which left us able to plug them into our partial view with respect to s equation and get the final answer of 192. Thank you.